Hello guys, my name is IBM and I'm taking you through IGCSE physics. This is still space physics and this is I think going to be lesson 3. Just remind you of the course outline of IGCSE for those who are doing IGCSE. You must go through motion, forces and energy, thermophysics, waves, electricity and magnetism. You must go through nuclear physics and then space physics, and currently I'm recording space physics. I started with the space physics because I just wanted my students to catch up with the time so that we finish the syllabus earlier so they can watch the videos ahead of the class, ahead of time, so that as I cover the other remaining topics, for them they will be covering at least one topic ahead of me. So let's go to space physics lesson 3. So this is space physics IGCSE and this is going to be lesson 3. Lesson 3, just to remind you, in lesson 1 we talked about the earth, phases of the moon, the seasons, we talked about day and night. Then lesson 2 we talked about the solar system, we talked about the planets, the inner and the outer planets. We talked about the gravitational pull of the sun, which is responsible for the rotation of the earth around the sun and other planets. We talked about the objects which make up our solar system entirely. We talked about the energy conversions or energy transfer between the gravitational potential energy and kinetic energy, and so on and so forth. So in lesson 3, I want us to talk about the sun, and then I think we shall talk about the sun as a star, and we shall talk about stars in general. So let's start with the sun as a star. So the syllabus has the following learning objectives for students doing core. Under the sun as a star, you should know the sun is a star of medium size, consisting mostly of hydrogen and helium, and that it radiates most of its energy in the infrared, visible, and violet. So these are very important. Uh, the sun is made up of majorly hydrogen and helium, and it radiates most of its energy in the infrared, visible, and ultraviolet regions of the electromagnetic spectrum. Then for a student doing extended physics, they should know that stars are powered by nuclear reactions that release energy, and that in stable stars, the nuclear reaction involved the fusion of hydrogen into helium. So hydrogen fuses into helium. So that is what the extended student should be knowing at the end of this part of the sun as a star. Okay, so let's talk about our sun in more details. Our sun in more details. So like I have already mentioned in the objectives, the sun is a medium-sized star which lies at the center of the solar system. It is considered to be at the center of the solar system. Remember, when the accretion disk was formed, the dust and gas which were pulled towards the center became hotter and hotter and hotter and then our sun was formed. Hotter and denser, and our sun was formed at the center of our solar system. And the sun is believed to consist of about 75% hydrogen and 24% helium. And of course, the 1% are comprised of other elements such as oxygen and carbon. So the biggest percentage of the sun is mostly hydrogen, 75%, and helium, 24%, makes up our sun. Of course, the sun, as mentioned earlier on, also radiates energy, mostly in the infrared. About 50% of the energy radiated by the sun is in the infrared region of the visible spectrum. Remember, the visible spectrum ranging from Menela's mother or Reed's mother is visiting Uncle Xavier's garden. This is the electromagnetic spectrum. So R standing for radio, micro, infrared, visible, ultraviolet, X-rays, and gamma rays. So 50% of the energy radiated by the sun falls in the infrared, around 40% falls in the visible light, and around 10% follows in the ultraviolet. So Basically, the sun bathes us with this range of radiations: infrared, visible, and ultraviolet regions of the electromagnetic spectrum. And this energy comes from what we call nuclear fusion. Nuclear fusion reactions, or nuclear reactions of hydrogen nuclei, which combine to form helium in the core of the sun. So the process responsible for the energy of the sun is actually nuclear fusion. And the Earth's atmosphere absorbs a lot of this ultraviolet radiation almost every day. And we have the ozone layer, which is in particular responsible to absorb the most harmful ionizing radiations, or the most harmful ionizing ultraviolet radiations, or ultraviolet rays within the atmosphere. Let's briefly talk about nuclear fusion in stars, because we have said the nuclear fusion is responsible for the energy which is generated by our sun. So all stars that we are yet to talk about later on are powered by nuclear reactions that release a huge amount of energy. Stable stars like our sun, which fall in what we shall call the main sequence, the stable stars are powered by nuclear fusion, or sometimes called thermonuclear fusion, where hydrogen uh, where hydrogen fuses into helium. So it is nuclear fusion that is responsible for the energy of our sun. What is nuclear fusion? Nuclear fusion, a concept mentioned in nuclear physics, is a reaction in which a lighter nuclei, which are in this case are going to be hydrogen, combine to form a heavier nucleus, which in this case is going to be helium. That's what we call nuclear fusion. Fusion is like to come together. So two lighter nuclei, which are most likely deuterium or hydrogen, the isotope is called deuterium, they tend to come together. In the process of coming together, they form a heavier nucleus called helium, and this process is accompanied by emission of energy. The process is accompanied by the emission of energy. So stars are considered to be a huge ball of mostly hydrogen gas. Mostly hydrogen. Remember, I said of 75% of our sun is made from hydrogen, or is made up of hydrogen, and around 24% is helium. So in the core, or in the center of a star, hydrogen nuclei undergo nuclear fusion to form helium nuclei. An equation for a possible fusion reaction could be the following here, where this is an isotope of hydrogen called deuterium. Of course, this is another isotope of hydrogen called tritium. These ones can combine because they are lighter. They can combine to form a relatively heavier nucleus called helium. And in the process, a vast amount of energy accompanies this reaction. So deuterium combines with the tritium. These ones are both isotopes of hydrogen. So they are formed through other fusion. Of course, they are formed through other fusion reactions, which we are not supposed to talk about at this level. So I want us to note, one, nuclear fusion requires very high temperatures and pressures to overcome the repulsion between the positively charged nuclei. Note that a hydrogen nucleus, which is say H21, is coming together with a tritium, which is also hydrogen nucleus, but an isotope of hydrogen, which is H31. These are both positively charged nuclei, and like charges are bound to repel. So because these ones repel, for them to be able to combine or to fuse to form helium, there should be a strong, there should be a lot of work to overcome the force of repulsion. So high temperatures means that these nuclei have high kinetic energy, so they can move very close to each other. They can move so as to fuse in order to overcome the force of repulsion between them for fusion to occur. So nuclear fusion requires a very high temperature and pressures to overcome the repulsion between the positively charged nuclei, which are coming together. Because they have like charges, they are bound to repel. And because we know that they are bound to repel, for the fusion to occur, for them to come closer together, the force of repulsion must be overcome. This means they should have a lot of kinetic energy. That's why it is only possible at a very high temperature, because high temperature means high kinetic energy of these nuclei. So they can overcome the force of repulsion for fusion to occur. The surface temperature of the sun is about 5,800 Kelvin. That is the surface. But of course, the sun's core has a temperature of about 15 million Kelvin and a density of about 150 times that of water. Remember, the density of water is around 1,000 kilograms per meters cubed. So the density of the core of the sun is about 150 times this one here. That means it is extremely dense. The Earth orbits the sun, as we mentioned earlier on in lesson 1, at a distance of around 150 million kilometers, that is 1.5 times 10 to the power of 11 meters, which is within the habitable zone, that is within the zone within a zone where life is possible. So this is the zone where water can exist in a liquid form, an essential requirement for life as we know it. So about 1.5 times 10 to the power of 11 meters, that is a habitable zone where water is possible to exist as a liquid. If it was hotter, the water vapor would never condense. If it was colder, ice would never melt. So it is just good enough for water to exist as a liquid. One important thing we also need to note is the mass of our sun. The mass of our sun is around 2 times 10 to the power of 30 kilograms. And this is what we call the solar mass. The mass of the sun is what we call the solar mass. Remember, in lesson 2, we mentioned that the sun comprises of about 99.8% of the mass of our solar system. So it makes sense for us to call the mass of the sun the solar mass, because the mass of our solar system, 99.8% is taken up by the mass of the sun. So the remaining parts of the solar system just contribute around 0.2%. So that is our sun. We have talked about what it is entirely made of: 75% hydrogen, 24% helium. We have also talked about most of the energy it radiates to be falling in the infrared, 50%, visible light, 40%, ultraviolet, 10%. We have also talked about the energy being produced by the sun coming from nuclear fusion reactions, where hydrogen nuclei basically combine or fuse. They come together to form helium, and in the process, energy is supplied. So it means we qualify for a short self-check about the sun. Name the process that makes stars, stable stars such as our sun, to shine. So we have mentioned the process is nuclear fusion. From which two elements is the sun mostly made of? We mentioned hydrogen and helium. Give an approximate value for the temperature of the sun's surface, 5,800 Kelvin. The solar mass is 2.0 times 10 to the power of 30 kilograms. The temperature of the sun's core is around 150. It's around 100 and it's around 15 million, Kelvin. That is the temperature of the core of the sun. Then the percentage of the sun that is in the infrared, I think infrared is 50%, visible is around 40%, and ultraviolet is around 10%. So that is a short self-check about the sun. That is our sun. Then next we should be talking about the stars in details. So let's talk about stars and galaxies. So according to the syllabus, I also saw that a student should know the following. For core students, the learning objectives include: state that galaxies are each made up of many billions of stars. For example, the Milky Way galaxy is made up of billions of stars. Also state that the sun is a star in the galaxy known as the Milky Way galaxy. Other stars that make up the Milky Way are much farther away from the Earth than the Sun is from the Earth. That's why we don't actually see them, because they are much farther away from the Earth than the Sun. We see the Sun because this is the closest star. Then also state that astronomical distances can be measured in a unit called light years, where 1 light year is the distance traveled by light in space or by light in 1 year. Then for extended students, they will be able to know that 1 light year is equal to 9.5 times 10 to the power of 15 meters. Describe the life cycle of a star. A star is formed from interstellar clouds of gas and dust that contain hydrogen. A protostar is an interstellar cloud collapsing and increasing in temperature as a result of its internal gravitational attraction. A protostar becomes a stable star when the inward force of gravitational attraction is balanced with the outward force due to high temperature in the center of the star. All stars eventually run out of hydrogen as fuel for the nuclear reaction. Most stars expand to form red giants, and more massive stars expand to form red supergiants when most of the hydrogen in the center of the star has been converted to helium. A red giant from a less massive star forms a planetary nebula with a white dwarf star at its center. A red supergiant explodes as a supernova, forming a nebula containing hydrogen and new heavier elements, leaving behind a neutron star or a black hole at its center. The nebula from a supernova may form new stars with orbiting planets. So this is the life cycle of stars that we are going to talk about later on. Describe the life cycle of a star. A star starting as interstellar clouds of gas, a protostar, we shall talk about stars running out of hydrogen, and they either form red giants or red supergiants depending on the mass. So after a star becomes stable, its path is going to be determined by its size, whether it becomes a red giant or a red supergiant, as we shall see later on. So let's talk about stars and galaxies. Stars and galaxies. And before we talk about stars and galaxies in more details, I want us to first understand the astronomical distances. Astronomical meaning in space. Objects in space are called astronomical objects. So astronomical distances must be those distances of objects in space. Those astronomical distances that we're going to talk about here. So our distances in the solar system are almost unimaginably big. The Earth is approximately 150 million kilometers from the Earth, from the Sun, which is 1.5 times 10 to the power of 11 meters. This is similar to circling the Earth about 4,000 times. Imagine cycling around the Earth 4,000 times, and the radius of the Earth is around 6,400 kilometers, I think. That is the radius. So now imagine cycling around the Earth 4,000 times. So this distance of 150 million kilometers is a very big distance. So when you look into the night sky, the light you see from the stars has been traveling for many years. It has been traveling for many years, especially for stars which are extremely far away from each other, from us. Since the light travels at a speed of around 3 times 10 to the power of 8 meters per second, this is considered to be the universal speed limit. The speed of light is the universal speed limit, and we believe that nothing can travel faster than this speed. However, if we compare to large astronomical distances, then light travels relatively slow. That's why in lesson 2 I mentioned that when you turn the lights on, you see it as if light appears instantly simply because it is traveling a very short distance. But if light is to travel an imaginably very big distance, then we say that it is relatively going to be slower because of the bigger distance it is going to be traveling. So astronomers use this idea as a way of measuring very vast distances. And therefore, it means that astronomical distances, such as the distances between stars and galaxies, are so large that physicists use a physical unit, a special unit, to measure them, and this special unit is called the light year or light years. So, the distances are often expressed in terms of how long it takes light to travel. How long it takes light to travel, that is called the light year. So rather than measuring the distances in meters, because the distances are extremely large, another unit called the light year is used to express these large distances. So let's talk about the light year in more details. So we have mentioned that a light year is the time, is the distance traveled by light in 1 year. A light year is a unit of distance. Unimaginably very large distances are converted in more convenient units, or in a more convenient unit called a light year. So a light year is a measure of distance, it's not a measure of time. So we say that a light year is the distance traveled by light in a vacuum in a time of 1 year. The distance traveled by light through space or in a vacuum in a time of 1 year is what we call the light year. Remember from your previous topics, especially motion, forces, and energy, distance was obtained from speed times time. And because we have said the light year is equal to the distance traveled by light in 1 year, and distance is speed times time, which is 1 year. So 1 light year is equal to speed of light in a vacuum times 1 year in seconds. That is 1 light year. So if I convert this, our speed is 3 times 10 to the power of 8 meters per second. Then I'll change the 1 year in seconds becomes 365. You may not add the 0.25 times 24 hours times 3,600 seconds. So this is the time, which is 1 year. So this is distance traveled by light in 1 year. So that is distance times time. And when I press my calculator, 3 times 10 to the power of 8 multiplied by 365.25, or just 365, times 24 hours times 3,600, to change it to seconds. So this gives me 9.5 times 10 to the power of 15 meters. So as an extended student, you need to note that 1 light year is equal to 9.5 times 10 to the power of 15 meters. Think about the next star to us after the sun, which is called the Proxima Centauri. The Proxima Centauri is about 4.2 light years away from the Earth. If you were to try and change this to meters, if 1 light year is 9.5 times 10 to the power of 15 meters, so Proxima Centauri is going to be 4.2 times 9.5 times 10 to the power of 15 meters from us. That is the nearest star to us after the sun. So this means it would take light from Proxima Centauri about 4.2 years to reach us. That's what it means. And the diameter of the Milky Way, which we are going to talk about later on, is approximately 100 light years, which would mean it would take about 100,000 years for light to travel across our Milky Way galaxy. Here is an example. The center of our galaxy, which is the Milky Way, is 30,000 light years away. How long would it take light to reach the Earth? Because the center of our galaxy is 30,000 years away, it means it takes light 30,000 years to reach the Earth from the center of our galaxy. And if our 1 light year is 9.5 times 10 to the power of 15 meters, then we can find the distance in kilometers. So it takes 30,000 years to reach the Earth from the center of our galaxy, because our center is about 30,000 light years. And remember, 1 light year is 9.5 times 10 to the power of 15 meters. To change it to kilometers, I divide by 1,000. 9.5 times 10 to the power of 15 meters. To change to kilometers, I divided this by 1,000, which becomes 9.5 times 10 to the power of 12 kilometers. So that is the distance for 1 light year. So that means 30,000 light years is going to be 30,000 times this distance here. That's why I multiplied here. I will just check if I got the correct answer. 30,000 times 9.5 exponent 12. So this distance was correct. That is how we use the light year. The distance traveled by light in 1 year is called a light year. Let's talk about the galaxies. Remember, we are talking about stars and galaxies. So we have defined another unit to be used for very large distances or the very large astronomical distances, which I have called the light year. Let's briefly talk about the galaxies. So the universe is a large collection of billions of galaxies. So the universe is made up of billions of galaxies. However, a galaxy is a collection of billions of stars held together by gravity. A galaxy is a collection of billions of stars, which stars are held together by gravity. Our sun is one of many billions of stars in our galaxy, which is called the Milky Way. So our galaxy is called the Milky Way, and our sun is one of those stars which are in the Milky Way galaxy. But because our sun is in our solar system, we are more familiar with our sun than other stars. So there might be about 200 billion stars in the Milky Way, about 20 stars for every person on Earth. So every person on Earth would have 20 stars if there are about 200 billion stars. Because the population is about, I think the population is about 20. Is it about 10 billion people? So we have about everyone would have about 20 stars if for every person on Earth. Other stars that make up the Milky Way are much farther away from the Earth. That's why we don't even see them. Remember, I said the next star after the Sun is the Proxima Centauri, which is also about 4.2 light years away from the Earth. Some of these stars also have planets, but we don't talk about such planets because we believe maybe they are not in a habitable zone. So life is not possible on such planets. The Milky Way is a spiral galaxy. So our galaxy, which is the Milky Way, is a spiral. You can say spiral. It is a spiral galaxy like that. It is a spiral galaxy with a central bulge. With this, so the center bulges as shown in this figure here. So this is how we would represent it. As a spiral would represent like this, but physically it would be represented like this with a central bulge at the center, which we normally call the nucleus, with the central bulge as shown in the figure. Our galaxy, the diameter of our galaxy, which is the Milky Way, is about 100,000 light years. So the distance from one end to another end is about 100,000 light years from one end to another end. Of course, from the center to the other end is considered to be between 20 to around 50,000 light years. And our solar system is located at about 30,000 light years from the center. So our solar system could be somewhere at around 30,000 light years from the center. That means it would take around 30,000 years for light from the center of our galaxy to reach our solar system or to reach our Earth. Because the Earth is on our solar system and the center is around 30,000 light years from the galactic center or the center of the galaxy. That is two-thirds of the way along a spiral arm with the sun at the center of our solar system. So the sun is considered to be at the center of our solar system somewhere here. So our galaxy is around 100,000 light years in diameter. and it is about our solar system is about 30,000 light years from the center of our galaxy. Remember, one light year is equal to 9.5 times 10 to the power of 15 in meters. The Milky Way is spinning, and it takes our solar system about 225 million years to travel once around the galaxy. So our Milky Way galaxy, or the home to our solar system, which is the Milky Way, is actually not in one place. It is actually spinning, and it takes our solar system 225 million years to travel once around the galaxy. So that is our galaxy. Let's talk about the stars again. Let's talk about star formation. How are stars formed? So our stars go through a sequence of evolutionary stages, which we shall call the life cycle, or the life cycle of a star. And all stars follow the same initial stages. That is, the first three stages are: a star starts as a nebula. We said a nebula is an interstellar cloud of gas and dust. Then it becomes a protostar. So the first stage is normally considered to be a protostar, which is the first stage of a star, where the nebula collapses. And when a protostar is formed, it becomes a stable star when the gravitational attraction within the nebula, or the gravitational attraction force, becomes equal to the outward force due to the high temperature at the core. Then the star becomes a stable star. So these are the first initial stages of every star. Then after these three stages, the next stage will depend on the mass of the star which is formed. So what is a nebula? First of all, when we talk about a nebula, all stars form or are born from a giant interstellar cloud of gas and dust, and this is called a nebula. It basically contains hydrogen. Mostly, the biggest percentage is hydrogen. So this is called a nebula. Sometimes it's called a molecular cloud, which are both cold, dense enough for star formation. So the major characteristic of the nebula is that it is cold, or the major characteristic of the molecular clouds is that they are cold and extremely dense enough for star formation. So all stars are born from interstellar cloud of gas and dust that contain majorly hydrogen. Then from the nebula, now the first stage, what is considered to be the first major stage of the star is formed, which is actually the protostar. So the star now starts as a protostar. What happens, or what leads to a protostar being formed? The gravitational attraction within a nebula pulls the hydrogen gas molecules closer together, and their gravitational potential energy is transferred into kinetic energy. So as the hydrogen gas molecules are pulled close to each other, when they come closer, they lose their gravitational potential energy. Remember, gravitational potential energy is maximum at infinity. So when the molecules are brought closer together, they lose their gravitational potential energy and they gain kinetic energy. So the gravitational potential energy is transferred into kinetic energy. And as these molecules collide, their kinetic energy is again transferred into thermal energy. So heat is generated. When the molecules collide, their kinetic energy becomes thermal energy. So the energy changes are gravitational potential energy to kinetic energy to thermal energy, or to heat energy. So the clump of hydrogen, the clump of gas and dust, then now contracts into a spinning sphere of super hot gas, which we call a protostar. So the gravitational attraction within the nebula is pulling the hydrogen gas molecules closer together. And these hydrogen gas molecules lose their gravitational potential energy as they gain kinetic energy. So when they gain the kinetic energy and collide, their kinetic energy is transferred into thermal energy. Therefore, the clump of gas contracts into a spinning sphere of super hot gas, which we call a protostar. So the collapse of a nebula is what is resulting into what we are calling a protostar. So this, as the particles are pulled closer together, the density of the protostar increases. So the protostar becomes denser and denser as the particles are pulled together. So this results in more frequent collisions between the particles, which cause the temperature to increase. So as the protostar is being formed, the molecules or the particles are colliding and their kinetic energy is changing into thermal energy, resulting into a super hot dense ball or spinning sphere of super hot gas, which we are calling a protostar. And as more frequent collisions occur, the temperature of the protostar which is formed continues to increase. The temperature continues to increase, and therefore the next stage of star formation now comes in. So what is the next stage of star formation? So after the protostar now, some forces must be balanced for us to come up with a stable star. So after the protostar, remember I said a protostar is an interstellar cloud collapsing and increasing in temperature as a result of its internal gravitational attraction. We said uh, the gases, the clump of gases collapse, the clump contracts into a spinning sphere of super hot gas known as a star because the gravitational attraction within the nebula has pulled the hydrogen gas molecules closer together. So in other words, the interstellar cloud is collapsing. And as it collapses, the gravitational potential energy is transferred to kinetic energy. And as the molecules collide, the kinetic energy is transferred to thermal energy. Therefore, a protostar is like an interstellar cloud collapsing and increasing in temperature as a result of the internal gravitational attraction of these particles or of the hydrogen gas molecules which are coming closer together. So now a stable star therefore must be formed after the protostar. So how is a stable star formed? Stable stars are sometimes called a main sequence star. So when a star is born, it immediately moves to what we call the main sequence. The main sequence where most of the stars are formed or where most of the stars are found. So a protostar becomes stable when the inward force of gravitational attraction is balanced by an outward force due to the high temperature in the center of the star. As the hydrogen molecules are being contracted or pulled together and losing their gravitational potential energy, which is being transferred into kinetic energy, which kinetic energy is being transferred into thermal energy, a lot of heat is generated at the center or at the core of this protostar. As heat is generated at the core of the protostar, the temperature of the protostar increases, resulting into what we call radiation pressure. So this results into an outward force, which we call the radiation pressure due to the high temperature in the center of the star. So now we have two forces. One is acting inwards due to the gravitational pull, which is attracting the hydrogen molecules together. And then one is acting outwards due to the high temperature, which has already been created at the core of the star. Once these two forces balance, a stable star is formed. So we call this stage a stable star or the main sequence star. So once the protostar becomes hot enough, nuclear fusion reactions occur within its core. So the hydrogen nuclei fuse, they are combining. The hydrogen nuclei will fuse to form helium at the core, and every fusion reaction releases heat. That's why the temperature of the core is becoming hotter. The kinetic energy of the molecules is being transferred into thermal energy. So once a star initiates fusion, it's known as a stable star. So as soon as fusion starts, it means the outward forces are now balancing with the inward forces because heat can be generated from the center of the star. Heat can be generated from the core of the star, resulting into an outward force, which when it balances with the inward force due to gravity, the star becomes stable. So once a star initiates fusion, it is known as a stable star. And during this stage, the star is in equilibrium as the forces acting on it are balanced. We have said the forces which are acting are the gravitational attraction force, which acts inwards. This one pulls the outer layers inwards. It pulls everything around the star inwards. That would cause collapse. That caused the collapse of the interstellar clouds initially when we had just a protostar. But then, as the collapse occurs, the particles which have been pulled inwards, losing their gravitational potential energy, we have said they gain kinetic energy, and the kinetic energy is actually lost or transferred to heat, thereby initiating nuclear fusion at the core of the star or at the center of the star. And this nuclear fusion also generates a lot of heat or releases a lot of heat at the core of the star, resulting into what we call the radiation pressure or the thermal pressure due to the high temperature at the core of the star, which acts outwards. So this is exerted by the hot gases, by the expanding hot gases inside the star as energy is released during nuclear fusion. So during nuclear fusion at the core of the star, then radiation pressure or thermal pressure, which acts outwards, is generated. And once these two forces, one due to the high temperature at the core, which we call the thermal pressure or radiation pressure, and one due to the inward gravitational attractive force, once these two forces balance, then we have a stable star. Briefly, let's talk about the radiation pressure. So hot bodies radiate heat, and this radiation exerts a force we have already called the radiation pressure. Once the object is hot, it gives out heat, and this radiation is normally called a radiation pressure. If the object is hotter or the hotter the object, the higher the radiation pressure. So that means as the gases collapse into the core and fusion occurs, generating more energy at the core becomes hotter and hotter, meaning the radiation pressure at the core increases until a point where it balances with the gravitational attraction, the inward gravitational attraction. So a radiation pressure acts outwards, making the star to expand, and in the opposite direction to the force due to gravity, the force of gravity pulling the star inwards, making the star to contract. So the force of gravity pulls the star inwards, so it contracts the star, while the radiation pressure or the thermal pressure acts outwards, making the star to expand. So these two forces must be balanced for the star to become stable. So when the forces are balanced, the star is said to be stable. I want you to note that as the core temperature increases, radiation pressure increases. The star increases in size, it expands. And if the core pressure decreases, the star shrinks when the core temperature falls. That's why I said initially we start with the collapsing gases into the core, collapsing gases due to the inward gravitational attraction. The gases lose their gravitational potential energy as they gain kinetic energy. The kinetic energy is then transferred to thermal energy at the core. Once the temperature of the core is high enough, now fusion of the hydrogen gases occurs, again generating a lot of heat. So this heat results into what we call radiation pressure, which acts outwards. And once these two forces, the inner gravitational pull and the outward force due to the energy released during fusion, once these two forces balance, the star is said to be a stable star. So here is a simple illustration of the two forces, the two balanced forces in a stable star. So assuming that this is the core, we have two forces now. Initially, we started with the inward pull, the inward gravitational attraction force, which was causing the interstellar cloud to collapse inwards. But I said as the gases collapse inwards, they lose their gravitational potential energy and gain kinetic energy. The kinetic energy is transferred to heat. The heat energy now makes the core to be extremely hot and fusion reaction can be initiated. Once fusion reaction is initiated, then the outward forces due to the energy released during fusion can now come into play. And the outwards and inward forces within a stable star are in equilibrium for a stable star. They become equal for a stable star. So the center red circle, this one is representing the core of the star, and the orange circle represents the star's outer layers. And once a stable star is formed, the final stage of its life cycle is going to depend on its mass. So after the nebula collapsing into a protostar, the protostar then becomes a stable star once nuclear fusion is initiated. And once a stable star is formed, after that, the next stage of its life cycle is going to depend on the mass of the star, whether the mass is very big, several solar masses, or a few solar masses. So in summary, here is the life cycle of a star. So a star starts as a nebula or interstellar nebula or the stellar nebula, which is sometimes called a molecular cloud. Then the molecular cloud, which is cool and dense, collapses into a protostar, and it collapses into a protostar. When it becomes a protostar, as soon as fusion is initiated, it now becomes what we call a stable star or stable main sequence star. Then here, there are stars which have 8 solar masses. Remember, solar mass is the mass of the sun, because we said our solar system, the sun takes 99.8% of the mass of our solar system. So the mass of the sun is considered to be the solar mass. So there are those stars with less than 8 solar masses, like our sun. And there are those stars with more than 8 solar masses. So after the main sequence, after the star is stable, the main sequence, after the star is stable, the next stage of its life will depend on its mass. Those stars which are less massive will take this path. They will become red giants, they will become planetary nebula once they run out of fuel, and then they become white dwarfs or blacker dwarfs later on. If the star is very massive, that is, it has more than 8 solar masses, then it becomes a red supergiant. Then after it becomes a supernovae, which later becomes either a black hole or a neutron or a black hole. So the paths will depend on the mass of the star which has been formed after a protostar becomes a stable star. And I want us to first talk about the life cycle of low mass stars similar to the sun or similar to our sun. Life cycle of low mass stars similar to our sun. So our sun is a low mass system, and like we said, we start with the interstellar cloud, which is a nebula or the molecular cloud. Then it becomes a protostar, where when it initiates fusion, it becomes a stable star, which goes to the main sequence. So here it is stable. And because it is a low mass star, then it will become a red giant. It will become a red giant. Then now, when it runs out of fuel, it becomes a planetary nebula, which later on becomes a white dwarf or a black dwarf. So all stars will begin as protostars when the nebula collapses. But like I said, the future path of a star is determined by its mass when it moves on to the main sequence. A stage in its life when it is stable and burning hydrogen. So the main sequence, when the stage that is the stage when the star is stable and is burning fuel, which fuel is actually hydrogen. A low mass star, like I have mentioned, which is similar to our sun, later becomes a red giant, and when it runs out of fuel, it becomes a planetary nebula and a white dwarf, and finally a black dwarf. By the way, just to mention, our Sun is about halfway through its time as a stable main sequence star. It will become a red giant in the next 5 billion years from now, when it will expand beyond Earth's orbit. So we still have more time for our Sun to become a red giant. So it has about 5 billion years from now. So in summary, the major stages for the life cycle of a low mass star, we start with the stellar nebula or the interstellar nebula, or you can call it the molecular cloud, which collapses into a protostar. And when a protostar initiates fusion, it becomes a stable star or the main sequence star. Because this is a low mass star, it becomes a red giant, which when it runs out of fuel, it becomes a planetary nebula, which later on becomes a white dwarf and then a black dwarf. By the way, before I may forget, low mass stars like our Sun, these ones live longer than high mass stars because the low mass stars use up their fuel very, very slowly. So low mass stars live longer because they use up their fuel or their energy, their hydrogen very, very slowly compared to very massive stars which rapidly use up their fuel. So, having seen the nebula, we have seen this protostar, we have seen the stable star. Let's just talk about the red giant, because we said after the three stages, after these basic three, the stellar nebula, where the dense, where we just have a dense and cool interstellar cloud of gas and dust, which then collapses into a protostar, where when it initiates fusion, it becomes a stable star. Because this is a low mass star, our next stage is going to be the red giant. What happens in the red giant stage? So after several billion years, the hydrogen in the core begins to run out. And once this happens, the rate of fusion decreases. Remember, the stable star, when the star is stable, it is very active, it is burning its hydrogen. But after several billion years, the hydrogen in the core now begins to run out. And as the hydrogen begins to get used up, the rate of fusion also decreases because the nuclei which are responsible for fusion have reduced. And as the energy produced by fusion decreases, it means, remember we said there are two forces acting when the star is stable. We have the inward star, which is due to the gravitational pull, and we have the inward force due to the gravitational pull and the outward force due to the radiation pressure. So as the star runs out of fuel, the fusion reaction decreases. It means the energy produced by fusion decreases, which means the inward force due to gravity now starts becoming greater than the outward force due to the radiation pressure. What is the effect? Of course, because the inward force is greater, it means the star must collapse inwards, it must shrink. And as it shrinks inwards, it heats up again. Eventually, because it has collapsed inwards, the core becomes hot enough again for helium to fuse into carbon. Because as the core collapses inwards again, the gravitational potential energy is converted into kinetic energy of the molecules, which again are transferred into thermal energy at the core. So as the core collapses inwards, the core becomes extremely hot, and that means helium, which had been formed previously during the stable stage, is now going to fuse into other elements such as carbon. Again, the energy released by reignited fusion reactions of the helium causes the outer layers of the star again to expand. So because now there has been reignited fusion reaction due to the helium fusing to form hydrogen, again the outer layers are going to expand. And as the star expands, its surface cools and it becomes what we call a red giant, which is a bigger star with a cooler surface. So initially we have said, um, after several billion years, the hydrogen in the core begins to get used up, and therefore the fusion reaction decreases. So the energy caused by the fusion reaction decreases, which means the inward force due to gravity exceeds the radiation pressure. So the core shrinks and heats up. When the core becomes very hot, the helium, which had been formed in the previous fusion reactions, also fused to form other elements such as carbon. The energy released by the reignited fusion reaction again makes the outer layers of the star to expand rapidly. As the star expands, its surface cools and it becomes what we call a red giant, which is a bigger star with a cooler surface. Then after the red giant, of course, remember it was already running out of fuel. Then we have what we call the planetary nebula. Once all the helium in the core also runs out, remember we started with hydrogen, which was fusing to form helium. Now, when the hydrogen got used up, we had helium, which fused to form carbon. Once the helium in the core also runs out, then now fusion reactions cannot continue. They have to stop. So here the star becomes again unstable, which means the radiation pressure decreases. Because it has run out of fuel, it is no longer generating energy from the core, so the radiation pressure now decreases, which means the core collapses under its own gravity. The core collapses inwards under its own gravity. The outer layers of the red giant are going to be blown away by the radiation pressure into space as a planetary nebula. So as the helium gets used up, as the helium gets used up, fusion reactions cannot continue, they actually stop. So the star becomes unstable. Radiation pressure decreases and the core collapses. Then the outer layers of the star are blown away by the radiation pressure into space as a planetary nebula. Then finally we form what we call a white dwarf. So the collapsed core of the red giant is called a white dwarf. The collapsed core becomes what we call a white dwarf. And the white dwarf may cool down, the white dwarf cools down over time. And as a result, the amount of energy it emits also decreases. So the collapsed core now becomes what we call the white dwarf. And the white dwarf will also cool down because remember fusion has already stopped and the amount of energy the core is emitting has reduced, and finally the white dwarf cools down over time, and as a result the amount of energy it emits also decreases because the core has already run out of energy. Has already run out of fuel to produce its own energy. So of course after a white dwarf it may become a black dwarf as it completely runs out of energy. Okay. Then let's talk about the life cycle of a very massive star. Stars with masses larger than or higher than the mass of our sun. Those are stars which have more than 8 solar masses, 8 times the mass of our sun. So we still have the same stages. We start with the interstellar nebula or the molecular cloud, which collapses into a protostar. And when fusion reactions occur, it becomes a main sequence star or a stable star. And after there, because it is a large star, then it becomes a red supergiant, which later on becomes a supernova when it runs out of fuel. And finally, it settles as a neutron star or a black hole. Remember, for the other one, we had a white dwarf and a black dwarf. Here it becomes either a neutron star or a black hole, as we shall see. So the stages are very simple: stellar nebula, protostar, stable star. It becomes a red supergiant, a supernovae, then a neutron star or a black star, depending on the conditions which are available. So since we have already talked about the stellar nebula, protostar, and stable star, which are the same stages for both, whether it is a large star or a small star, then let's talk about the red supergiant. For the light mass or the low mass stars, it was just a red giant. For the more massive stars, it is a red supergiant. After several million years, the hydrogen in the core also begins to run out, just like for the low mass stars. The star is hot for the fusion of lighter elements to continue in shells farther from the core, and the outer shell expands into a red giant. So hydrogen has started running out, but the star is too hot or is hot enough for fusion of lighter elements to continue in shells farther from the core, and the outer shell therefore expands into what we call a red supergiant. And during this stage, the core collapses because remember it was running out of fuel. So it means the inward forces were exceeding or the outward forces due to the heat at the core or due to the radiation pressure were reducing, and the inward forces were actually becoming or were greater than the outward forces. So the core collapses, and as it collapses, it expands rapidly as fusion reactions start and stop. So the core will always collapse and expand repeatedly because fusion will start and stop. Fusion will start and stop because as fusion goes on, or as the hydrogen in the core begins to run out, the star is already hot enough. So fusion in the outer areas or in the light of lighter elements will always continue in the shells farther away from the core, and that will cause the outer shell to always to expand. So during this stage, we are saying the core collapses and expands repeatedly. It collapses and expands repeatedly. Why? We shall talk about why it collapses and expands repeatedly. However, it is not possible to make elements heavier than iron by nuclear fusion. Just like we mentioned for the red giants, where the core collapsed, and as it was running out of hydrogen, then when it collapsed, helium fusion was initiated into other elements. Similarly, even here for the red supergiants, as the core collapses, helium fusion is initiated and other elements are being formed. And again, it collapses, another element fuses, and another element is being formed, and the process continues as the core expands and collapses repeatedly. However, it is not possible to make elements heavier than iron. So if fusion occurs and iron is formed, then nuclear fusion is going to stop. So once all possible fusion of elements has occurred, an iron core forms in the star and then fusion will stop. In fact, the star collapses in the star collapses in on its center one final time and then explodes as a supernova. So initially, as the core will always collapse and expand as fusion of lighter and lighter elements continues, fusion of different elements continues. But of course, every fusion element results into heavier elements. So once a heavier element such as iron is formed at the core, then fusion stops because it is not possible to form elements heavier than iron by the process of nuclear fusion. So the star collapses. Remember, iron is the most stable nucleus. If you look at very stable nuclei, iron is actually the most stable nucleus. So once iron is formed, then fusion reactions cannot occur anymore. So it means the star is going to collapse in on its center one final time, and then it is going to explode into what we call a supernova. So what happens after supernova then depends on the mass of the core that remained, or the mass of the core that remains. If the core is less than about 3 solar masses, very small. If the core is very small, less than about 3 solar masses, that is less than about 3 times the mass of the sun, our sun, then a neutron star forms. The force of gravity is so strong, and the electrons and the protons are forced together to create neutrons. So if the core is very light, about less than about 3 solar masses, a neutron star is going to be formed because the force of gravity is going to be strong enough to push or to make the electrons and protons combine and create what we call the neutrons. So we shall have what we call a neutron star. However, if the core is extremely massive, a more massive core will continue collapsing. If the core is extremely massive, it would continue collapsing until it becomes so dense that not even gravity, not even light can escape. So its gravity is going to be extremely high that not even light can escape. Therefore, it becomes what we call a black hole. So after the supernovae, which was formed in the final explosion, depending on the mass of the core that remained after the supernovae, then it either becomes a neutron star if the core is less than about 3 solar masses, or it becomes a black hole if the core was extremely massive. Therefore, it would continue collapsing until it becomes so dense and not even light can escape. So we say the star becomes a black hole. What is a supernova? Let's briefly talk about a supernova differently. So we have said that eventually fusion reactions inside the red supergiants cannot continue as soon as iron is formed. Fusion cannot continue when iron is formed. Initially, we started with hydrogen. When hydrogen is used up, the core collapses, and and then heavier elements such as helium, which are formed, then fuse to form others such as carbon. Once helium is used up again, carbon nuclei can fuse to form relatively again heavier nuclei, and the process continues until iron is formed. Once iron is formed, fusion cannot be possible for fusion of elements heavier than iron cannot be possible because iron is very stable. Iron is the most stable nucleus. After iron, other nuclei are going to be unstable. So eventually fusion reactions inside the red supergiant cannot continue once iron is formed. And at this stage, we say the core will collapse rapidly and is going to initiate a gigantic explosion, which we have called a supernova. At the center of the explosion, a dense body called a neutron star will form if the mass of the core that collapsed was less than 3 solar masses. The outer layers of the star are ejected into space, forming new clouds of dust and gas. So the outer layers of the star are going to be blown away into space, forming new clouds of dust and gas. And it is believed that it is from these clouds where other new stars can be formed and other planets. So the nebula from a supernovae may form new stars with orbiting planets. So the new clouds of dust and gas, which are ejected into the outer space, can be then the source for the new stars which can be formed in the future with their orbiting planets. The heaviest elements, that is, elements heavier than iron, are formed during a supernovae and are ejected into space. So these ones are not formed by nuclear fusion. And like I've said, the nebula may form new planetary systems because the nebula may act as the nebula which is formed from the supernovae may be responsible for forming new stars in the future with their orbiting planets. Then I said after supernova, then a neutron star could be formed or a black hole depending on the mass. And I said in the case of most massive stars, the neutron star that forms at the center will continue to collapse under the force of gravity into a black hole. That is for massive stars. For lighter stars, the core will not, if its mass is less than 3 solar masses, it just remains as a star. The gravity is just enough to force the protons the electrons and the protons to fuse to form neutrons, and it remains as a neutron star. But if the core was extremely massive, then the gravity is strong enough to make the core to continue collapsing, where it becomes dense that even light cannot escape its gravity. So it becomes what we call a black hole. So what is a black hole? A black hole is an extremely dense point in space that not even light can escape. That is what we call a black hole. It is extremely dense, a dense point in space that even light is believed not to be able to escape its gravity. Its gravity is so high that even light cannot escape. That is what we call a black hole. Okay. So from what I have said, or from what I have elaborated, you should be able now to answer a simple self-check. The sun is about 8 light minutes away. It takes sunlight about 80 minutes to reach the earth on its journey from the sun. Given that the speed of light is 3 times 10 to the power of 8 meters per second, how far away is the sun in kilometers? So you have the time, you have the speed, you should find the distance. How many years would it take a car to get to the sun traveling 120 kilometers per hour? So you know the distance. You have found the distance in part A. You should use it to find the time in part B. After our sun, Proxima Centauri is our next nearest star. It's about 4.2 light years away. How many seconds does it take light from Proxima Centauri to reach Earth? Because it's about 4.2 light years away, it would take 4.2 years for light from Proxima Centauri to reach us. How far away is Proxima Centauri in kilometers? So just change 4.2 light years into kilometers. Remember, 1 light year is equal to 9.5 times 10 to the power of 15 meters, which is the same as 9.5 times 10 to the power of 12 kilometers. Helios 1 and 2 hold the record as the fastest ever space probes at 252738 kilometers per hour, about 70 kilometers per second. How many years would it take these space probes to reach Proxima Centauri? Now that we know these ones are going to be leaving the Earth, and we know their speed is 70 kilometers per hour, the distance they are going to travel is 4.2 light years. So how many years are they going to take? You know the speed, you just change, you have already got the distance in kilometers in part B. You have the speed in kilometers per second. So you have to use time is equal to distance divided by speed. You have the distance from part B. The speed is given here. So you first get the time in seconds and then change it into years. Remember, 1 year is approximately 365 days. So you should change time from days to hours to seconds, and then you move backwards from seconds back to hours back to days. In other words, the answer you get, you're going to divide it by 365 times 24 times 3,600 to change it to years. How long would it take them to reach the nearest galaxy? 25,000 light years. So the distance is 25,000 light years. The speed is still 70 kilometers per second. So you just use the same time and you just use the same formula, time equals distance over speed. The distance is this one in light years, where 1 light year is 9.5 times 10 to the power of 15 meters, or 9.5 times 10 to the power of 12 kilometers. Then you can change it to kilometers because the speed is in meters per second. So this is going to be 25,000 light years, that is times 9.5 times 10 to the power of 12 in kilometers, divided by the speed, which is 70 kilometers per second. So my answer here is going to be in seconds. How long would it take? They didn't ask for the units, so I can leave my answer in seconds. Or you can change it to years. Make two sketches to show the Milky Way galaxy. One sketch should be the spiral, so we know the spiral, and the other should show the galaxy edge. So we saw that the galaxy bulges at the center, like this, where it is around 100,000 light years. On your sketch, mark the diameter of the Milky Way in light years. Of course, we know the diameter is around 100,000 light years. Mark the position of the Sun in the Milky Way. The Sun is around at the bottom here on one of the arms, around 30,000 light years from the center. How many stars are there in the Milky Way? About 200 billion stars. The solar system has existed 4.6 billion years. How many times has the solar system traveled around the Milky Way in that time? So you can now, because it has existed around 4.6 billion years, just look at the diameter of the Milky Way and then try to estimate how many times the solar system has traveled around the Milky Way. In other words, you need to estimate the time for one revolution around the Milky Way if its diameter is around approximately 100,000 light years. But this is equivalent to, okay, you can try to finish that. Assume that the average mass of a star is equal to the mass of the Sun. What is the mass of the Milky Way? Assume that the average mass of a star is equal to the mass of the Sun. What is the mass of the Milky Way? Because the Milky Way has over 200 billion stars, then I would multiply 200 billion stars times the mass of the Sun. What two properties do molecular clouds have that allow them to collapse? We say they are cool and dense. The interstellar cloud is cool and dense. This allows it to collapse. Explain how stars are formed. We have explained how stars are formed. What causes the center of a star to warm up when it forms? Of course, that is nuclear fusion. Okay. And finally, explain what is meant by nuclear fusion. Lighter nuclei coming together to form a heavier nucleus accompanied by emission of energy. Why can nuclear fusion only occur at high temperature? Because the nuclei involved have the same charge. So high temperature means high kinetic energy. Therefore, they have enough energy to fuse to overcome the force of repulsion for fusion to occur. Explain the following terms about the life cycle of a star. We talked about a protostar. A main sequence star is a stable star where the star is actively burning fuel, burning hydrogen. The red giant, that is for a low mass star. The white dwarf, when the red giant runs out of fuel. Then we talked about a supernova. Of course, the red giant burning out of fuel, forming a planetary nebula, which forms a white dwarf later on. We talked about the supernovae for the more massive stars, the neutron star. We talked about a black hole. That is an extremely dense point in space where even light cannot really escape. The gravity is so high that even light cannot escape that point. So I think that should be the end of lesson 3.
The moment I as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. One day I'll be yours.